Greetings from the New Horizon College of Engineering from Department of Civil Engineering. We have privilege to present you the video details related to the lab design and detailing of RCC structural elements. The code is CIV62. Design and detail of RCC retaining wall and structural walls. This will be covered in this session. Introduction. The main function of wall are to carry loads, enclose and divide the space, and exclude weather and retain heat. Based on these requirements, the following loads will be applied or will be acting on the walls. The load includes gravity loads, which is due to the slabs and beams, lateral loads, which may be acting perpendicular to the plane of wall due to wind and earthquake loading, water and soil loadings. These are the lateral loads that may be acting on the retaining wall systems or wall systems. Horizontal load in plane due to wind or earthquake may be acting. That is, along the longitudinal direction, wind loads and earthquake loads may be acting. This will, when the walls is used to provide lateral stability, as in the case of structural walls. For example, in case of shear walls, the walls may be subjected to horizontal in-plane loading. This may be due to wind load and or earthquake loadings. These are the basic definition to classify the wall. The first thing is, if the length of a wall, for example, if you talk about the length of my wall, for example here, length of a wall is more than 4 times the thickness of wall, then I can say it's a wall systems. That is, if length is more than 4 times the thickness, then I can classify this as a walls. So this is a basic definition for the wall systems. The load, it may be of gravity loads, as I described in the previous slide, load which may be coming from slabs and beams, etc. Next one is vertical plus lateral loads. It may be because of gravitational loadings and lateral loadings. This may be due to earthquake or seismic forces, or wind loads, etc. Third one, that is a D here, this may be subjected to vertical loading, that is a gravitation loads from slabs and beams, and lateral loading, that is may be due to wind and seismic loading, etc. Then the strength and behavior of a wall is normally depending upon the following criteria. What are they? The first thing is something called geometry of a wall systems. That is nothing but aspect ratio, slenderness ratio, and thickness ratio of my wall systems. Material property, that is it depends upon strength of concrete, steel, a mode of disposition of steels, that is I'm going for single layer or double layers. Steel ratio in vertical as well as horizontal directions. This composites or this relates to the material property of my wall systems. End conditions, it is nothing but fixed, free, or combination of these ends, etc. Loading pattern, that is the concentrated loads, uniformly distributed loads, axial loads, or eccentric loads, etc. Next thing, nature of openings, that is size and location of my size of my opening, for example door openings, window openings, locations, dislocation of opening, and symmetrical and unsymmetrical arrangements. That is, I may be having a symmetrical opening on both the cross sections or both the face of my cross section with refer to CG, or I may not having a same symmetrical arrangements. These things decides strength and behavior of my wall systems. These are the different types of RCC walls. The first thing is of a cantilever type of retaining wall, or this is what we are going to discuss here. Next thing is something about the counterfort type of retaining walls. That is, it will be retaining something, it may be of water, whichever is giving a lateral pressure, that will be retained. For example, here it is something called counterfort type of retaining walls. I have a vertical system, I have a horizontal base slab, it will be counteracted by this kind of counterfort slab systems. Next thing is something called load bearing wall, where the loads force will be acting in the vertical directions. Next thing is something called shear walls, where forces will be acting in the horizontal directions. That is what this is a conventional wall system which is subject to take care of lateral loadings. These are the some different type of RCC wall systems. So, slenderness and effective height of my wall. As per IS 456, class number 32.24, the wall system can be classified depending upon the slenderness ratio, and IS 456 has specified the effective height calculations that will be presented in the next table. So this effective height, that is slenderness ratio, is nothing but effective height by lateral dimensions. This decides the cross section, that is, this decides the cross section of my wall, which implies or which has an impact on stiffness. Slenderness ratio of my plain concrete walls may be depending upon effective length divided by thickness. That is, if I want to calculate about the slenderness ratio decides the stiffness. Slenderness ratio may be taken as effective length divided by thickness. If the cross walls are placed sufficiently close, horizontal distance between the cross wall may lead to effective length smaller than the usual effective height of my wall systems. So next thing, this table was taken from IS 456, which help us to determine the effective height. So based on effective height, we can able to classify the slenderness ratio. For example, if the wall has been restrained by floor systems, that is slabs both top and bottom, if there is a strain against rotation at both the ends, that is, if a wall is of a fixed type, effective length can be taken as 0.75 times HW. If a wall is not one end is rotation, that is, one end is being restrained against rotation, no rotation is being provided at both the ends, that is of a pinned type, 1 times HW, where HW is the unsupported length of a wall system can be taken. In case if a wall is being intersecting by number of lateral forces, then 0.75 times L1 and 1 times L, that is, it is nothing but the effective length of my wall systems. If intersecting walls or single walls is being provided, L1 is the unsupported length of my wall systems. This called row will talk about effective length of my wall. The first row will talk about effective height of my wall. So based on this, we can able to calculate the effective height of my wall or effective length of my wall, which determines the slenderness ratio. Next thing, detailing of concrete walls. So the spacing in both vertical and horizontal direction should not be greater than 3 times the wall thickness or 450 mm, whichever is less. Next point, for wall of thickness more than 200 mm, a vertical and horizontal reinforcement shall be provided in 2 grids, one on each face of a walls. For example, if a wall thickness is more than 200 mm, 2 layers of grids can be provided. Minimum of 16 mm bars should be provided in walls having 2 layers of reinforcements in both directions, and 116 mm bar in wall having a single layer of reinforcement in both directions around the window or door opening. Whenever I am having a door opening, the corners should be extra reinforced by providing minimum 1 number of 16 mm diameter bars. This diagram will talk about the reinforcement detailing of my walls. This is a plan view, or the first one is a general cross section of my wall. So you can see this, the vertical dots are the main reinforcements. The running system is of second reinforcements. So vertical reinforcement will be of a main reinforcement bars. The lateral bars will be of a second reinforcement bars. Second one is this B diagram. It is a vertical cross section of my wall. That is, if I cut here, the vertical bars will be the main reinforcement bars. Horizontal bars will be the second reinforcement bars. As we discussed in the previous thing, if the thickness of the wall system exceeds 200 mm, I should provide this kind of 2 layer of reinforcements. One at the inner face, one at the outer face. If I am providing two layer of reinforcements, the connection should be provided by means of clips. So clips in the sense, so in order to maintain the spacing between the bars, since if it bends, this outer layer, again this outer layer will be subjected to tension. To balance this, to keep the reinforcement in the correct position, we are supposed to provide this kind of clips which will flow in the both directions. Detailing of concrete walls. The standard concrete walls is being shown as shown next few slides. When only normal reinforcements are being provided, horizontal reinforcement may be placed inside and the vertical steels to reduce the possibility of coarse aggregate being hung up on the horizontal bars. That is, the spacing should be maintained such a way that coarse aggregate should not be hung up between the reinforcement bars. It is mandatory to provide the clips. Whatever we have seen in the last slide, we are supposed to provide the clips. And if there's additional, in addition, at all splices, top of each reinforcement bar, the bottom of each upper bar should be restrained by clips. The clips should be alternatively reversed, or else truss clips shall be provided, something like this. So if instead of providing one longitudinal clips, we can provide this kind of truss type of clips can be provided at the both top as well as bottom, which will hold this reinforcement bars in the correct positions. This will talk about some different type of retaining walls. Of course, you might have studied this in the theory classes. Just for understanding, first one is of a gravity retaining walls. Second thing is of an gabion type of retaining walls. The third thing is grip type of retaining walls. Fourth thing is T-type cantilever retaining walls. L type of retaining walls. Again, counterfort retaining walls and butt stress type of retaining walls. And this is the last one, anchor type of retaining walls. It has been anchored at the back side depending upon the active pressure or passive pressure. Next thing is segmental type of retaining walls. These are the different type of retaining wall systems that can be helpful for us to understand. Primary proportion of retaining walls. Before designing or before executing it, the proportion of retaining walls plays a very important role. So it has been decided or based on this, the area of steel also will be changing. So choosing the correct proportionate of retaining wall will place an effective design or effective place of reinforcements. The minimum depth of a foundation should be kept 600 mm from the existing ground levels. You can look at the figure here. From the ground level, the minimum of 600 mm depth should be maintained. The thickness of my slab should be h by 12 to h by 10, where h is the height measured from the base slab to the top hill. So let us see the different parts of my retaining wall. This is a vertical stem. This is something called base slab. In base slab, opposite to the retaining area, this is a retaining area. Opposite to this is something called toe slab. This is something called heel slabs. So if the total breadth of my base slab be B, then the B value can be 0.5 to 0.7 times h. Next thing, the toe slab dimension can be h by 8 to h by 5. Here, the heel slab can be h by 12 to h by 10. The thickness of my retaining wall be 200 to 300 mm. Next thing, the other direction, that is the height is the top thickness can be 200 to 300 mm. Next thing, the minimum height should be 600 mm. That is, minimum depth of my base slab from the existing ground level can be 600 mm. The B section, it will talk about the different cross section of my counterfort retaining wall. If you are interested, you can go through those things. We are not discussing about the counterfort retaining wall here in much in detail. Next thing, the primary proportion of retaining wall, whatever I explained here with the explained diagram, it has been shown here as a detail. You can please refer to those theory parts. Next thing is, this is the cross section of area that is to be provided. If as the height increases, area of steel what I provide in the stem portion can be reduced in such a way. This is an proportionate way of providing reinforcement. Ground level it is A, and middle part is 2/3 of A can be provided. Next thing is A by 3 can be provided. That is A, 2/3 of A and A by 3 at the top. So this way the area of steel can be provided from base to top levels. Behavior and detailing of cantilever retaining walls. The stem will act as a cantilever when it is subjected to lateral earth pressures. Critical section for maximum bending moment is at the junction of a stem and the base slabs. Shear may be critical in the stem as in the base slabs. Assumed thickness should be checked on reinforcement calculations. For higher and heavier load walls, greater thickness of concrete may be economical. Moment in the stem causes tension on the inside face where earth is retained, hence flexural reinforcement should be provided in this phase. For you can, it will be explained in the next slides. Thickness and the reinforcement can be reduced proportionate over the height. As the height increases, we can able to decrease the thickness of, that is, area of steel as well as reinforcements. Temperature reinforcement is provided transfers to the main reinforcements. That is perpendicular to the main reinforcement, transverse reinforcement will be provided. Nominal reinforcement should be provided in the vertical and horizontal direction near the front face, which is exposed to atmospheres. This is the behavior of my cantilever-retaining walls. When it is subjected to lateral pressure, that is the base slab will be, that is heel slab will be subjected to downward pressure, stem will be subjected to lateral pressure, toe slab will be subjected to upward pressures. So this area, if you see this two phases, that is this phase and this phase, will be subject to tension, and this phase of my toe slab will be subject to tension. So the reinforcement here, so this is subject to tension, so this fiber will be provided by reinforcements. Here this phase will be subject to tension, so here the reinforcement should be provided. This is the basic arrangement which we should provide when we are providing a reinforcement detailing for retaining walls. Design of base slabs. The design of toe slabs act as a cantilever in front of face of my vertical stem. It is subjected to upward pressure from the soil, and the sulfite will be acting downward as shown in the figure. The critical section for bending and the bending moment occurs at the face of my stem, whereas the critical section for shear force acts at the distance d from the face of a stem, where d is the effective depth of my toe slabs. Assumed thickness can be checked for adequacy, and required steel should be calculated. Next thing, the heel slab also acts as a cantilever. The lateral pressure tends to cause the retaining walls to rotate about its toe axis. The action tends to push the heel slab into backfill, making the weight of a backfill on the heel slab to push it down. Thus, heel slab is subjected to upward pressure from the soil and downward load due to sulfite and earth above the heel. The bending moment due to downward load is more than due to the upward loads. This causes tension in the toe slabs as shown in the figure. As already we have seen this in the diagrams. Each panel of a steel stem and heel slab should be subject between the two adjacent counterforts, may be designed as two-way slab systems fixed on 3 hinges and free on 4 sides. So this thing will talk about the design detail of my counterfort retaining wall systems. So since we counterfort retaining wall system is not under our scope, I am just keeping this. If you are interested, you can please refer to those things. Again, this is the pressure diagram. Of course, we have seen this. Just if you are interested, you can go through those things. The cross section, I have a heel slab, toe slab, the vertical stem, how the pressure is being given, something like this. So this will talk about the reinforcement detailing here. So the main reinforcement will be vertically kept vertical, and this is the second reinforcement bars. Net pressure which is acting downward, so top will be subject to tension. Again, opposite pressure, bottom tension. Again, the lateral pressure, tension in the both the sides. If the thickness increases, more 200 mm. If there is a failure against stability or overturning, this kind of shear key can be provided. The cross section of shear key and the area of steel what we provide in shear key can be matched equal to the reinforcements of what we provide in the stem. And these are the distributed reinforcement bars that is being provided. This is a critical or simple view of my cross area of steel what I provide for the retaining walls. So this is again the cross section and longitudinal section of your retaining walls. You can see this, the thickness is 200 mm at the top, bottom it is 450 mm. So I provide two layers of reinforcements. For example, I have a cantilever retaining wall systems. So the 16 mm at 150 mm is the main reinforcement bar. Second reinforcement bars are 10 mm at 250 mm. Next thing are the toe slabs, base slabs, heel and toe slabs. 12 mm at 200 mm is that main bars are being provided. Shear key is 450 by 450. This is the cross sections. So this is the heel slab, toe slab reinforcement is this one. And the main reinforcement 16 mm at 150 mm. Second reinforcement 10 mm at 250 mm. After 1.75 meter height, I can reduce the area of steel
So I have increased the spacing of main reinforcement. Instead of reducing the steel, I am increasing the spacing. It means that age of steel is decreasing. So up to the distance of 1.75 meter, it was 16 mm at 150 mm. Beyond for 1.75 meter, it has been reduced to 16 mm at 150 mm. The reinforcement spacings are 12 mm at 200 mm. So this will talk about the reinforcement, the elements. So this picture or this slide will give you the rough idea about the reinforcement detailing here. Next.
Thank you very much for listening to the video on reinforcement detailing on retaining walls with the main reinforcement, second reinforcement for stem, toe and heel slabs. Thank you for joining us.